All right, folks, so let's get started on chapter 2. Can you hear me? Let's turn this up. All right. So let's start chapter 2 and talk about atoms, molecules, and ions. So we just left chapter 1 looking at, how we use numbers, manipulate units, to look at, calculations, measurements, those things that you do in lab. So we're going to kind of take a big step in a different direction here within chapter 2 and talk about atoms and kind of what makes up an atom and some of the historical events that happened over time to help us come to the realization of what is the most our modern day, our modern view of our atom. So this chapter is real tough because how many people here know what an electron is? Like everyone, right? We know what an electron is. So it's like we already know the moral of the story. We already know the result. We already know that Darth Vader is Luke's father. But I'm up here trying to convince you, hey, these experiments are really important and changed our view of the model of the atom over time. So I want us here thinking about, like scientists, okay, how did the observations in each of these experiments, how are they significant in changing the atomic model one step at a time? That's the big idea here, and we will go into crazy detail about these experiments and the specifics about them. So we'll talk about atoms and the history, okay? So the idea, people always ask me, they're like, Dr. N, do I need to memorize the history? Of course, like, I wouldn't be teaching this if it wasn't a learning objective on the exam, all right? So yes, you do need to know these experiments, all right? But hopefully it's the conclusions we get from it is the most important thing here, all right? Then we'll look at the details of the elements on the periodic table, and then we'll go into naming. Remember, on the exam, you will always be given a periodic table. The thing is that there are no names on the periodic table. So what you see in this room is basically what you will get on the exam, right? See how there's no names, but there's symbols, okay? So you do need to know that if I say sodium, that is what element? Na, yeah, on the period. So you do need to know that. All the other numbers are given to you. Like sodium has an atomic number of 11. It gives you the atomic mass, things like that. But you need to know sodium is Na. So there are some weird ones. Like if I say antimony, do you know which one that is? Figure it out before the exam. All right. Did you have a question?
Yeah. Why would they give us one with names?
That's just how it is. All right. So yes. Okay, so let's get started. So the whole idea here with this first part of the chapter is historical events, how the view of the atom changed over time. And so we're going back in time to the day and ages of philosophers. The idea of like philosophy and sciences kind of overlapped in ancient times because it was the people who had enough money and free time to just sit underneath like a fig tree and like think about philosophy. Those were the people who were also thinking about scientific theories. All right, so the idea that there's kind of this overlap of philosophy and science in the ancient times. We'll see that they kind of deviate as time goes on and technology improves. So here are examples of 5 different atomic theories up here. We will talk about each and every one of these. The first line, the first 3 that you see, we'll talk about here just now in chapter 2. The last 2 down here, we will talk about in chapter 6. So you just have to be patient. So we will talk about this first line, how we go from each of these different models and how these specific experiments we'll talk about led to the next one. I just wanted to show the dates here. The dates aren't important. They're not important, but I just wanted to show you, okay, where do they show up in like the timeline of like humankind? So you see that like there's a huge gap between these first 2 theories, Dalton and our plum pudding model. But after that plum pudding model, And what we'll learn here is that this model came about because we learned, hey, there's something smaller than an atom, and that's a subatomic particle. Then progress happened real fast. That's why I show these dates here. But the dates themselves are not important. That is not a learning objective. I don't care about dates. I want you to know, hey, can you inspect these conclusions and come up with a good explanation or explain how the scientists came up with the conclusions they got. So we'll go through these three. That's chapter 2, and we'll move on to the Bohr model, and then finally the Schrödinger equation, which is the true model of the atom. And so, yes, we will look at this equation. Okay, we'll look at this equation. All right, so let's look at the first model, Dalton's model. So this model, again, has a footing in philosophy, where these philosophers, okay, I imagine they're Greek philosophers, like sitting under an olive tree, thinking about stuff, and they just think, hey, if I have an apple, and I cut that apple in half, is it still an apple? Okay, yes, yeah. What if I cut it in half again? Is it still an apple? And if I cut it in half again, is it still an apple? Yes, but like, what if I do that a million times, over and over and over and over? Like, philosophically, these thinkers thought there has to be a certain point where I cut an apple, like the part of the apple, into such a small unit, the smallest unit, that if I were to cut it again, it would no longer be an apple. All right, that it would lose its identity, it would lose its properties. That is essentially what Dalton's theory is saying, that elements like on our periodic table, the atoms of those elements are the simplest substance that you can have. That if you have like a piece of gold, you could cut it a billion trillion times to a certain point where if you cut it again, it's no longer gold. All right, so that was his idea, that the atom is the simplest form of an element, that it's just kind of this spherical ball. All right, a lot of the tenets of Dalton's theory is true, but there are some aspects that aren't true. So some of the true aspects are like, you can't convert oxygen to nitrogen. All right, that the whole, like, where chemistry came from in early civilization has roots in alchemy. Alchemy is the technique or the science to convert things into gold. They wanted gold. They wanted shiny things. So they took everything on the periodic table trying to turn it into gold. But what we learned is that you can't turn one element into another just by chemical means. You can use nuclear chemistry, but you can't use nuclear means to do that. So that was part of Dalton's theory, and it's somewhat true nowadays, that you can't convert one thing to another. Another thing is that if you have a sample of some type of compound, depending on the formula of that compound, you will always get that same mass ratio of atoms no matter where you find that sample. So this is the law of constant proportions. So like H2O, water, H2O is always two hydrogens, one oxygen, regardless of where you get that water. The mass percentages stay the same also. So that's Dalton's theory, okay? But this theory stuck around for a really long time. Folks were scared to basically, go against Dalton. Like, his theory was the theory of choice for over 100 years, okay? Until they discovered that, hey, there's actually something smaller than an atom, and that's a subatomic particle. Sub meaning smaller or beneath, a subatomic meaning smaller than an atom. So it took the discovery of subatomic particles to finally dismantle the hold that Dalton had on science, the scientific community. That it was like his theory that was kind of like reign supreme for hundreds of years, right? Until subatomic particles come along. So that's where we are now. Okay, so we're going to talk about a couple experiments here, so write these things down. This is the story of the electron. All right, I'm going to be talking about an electron here a lot, but like I asked already, like most of us know what an electron is, right? We know what it is. Humor me. Just take the knowledge you have about the electron, just put it in your back pocket for now. Just forget everything you know about an electron and just look at these experiments at face value and try to think about, okay, what kind of conclusions did these scientists come up with? So this is the first of two experiments relating to the electron. And so the first one is the J.J. Thomson's cathode ray tube experiment, or CRT. So CRT means cathode ray tube. Most of you have CRTs probably in your basement or your parents' basement. So CRT, cathode ray tube. Do you know someone who has like one of those big TVs with the big backs on them? Or if I say that, you know what I'm talking about, the big backs, okay? The ones where if you stick a magnet to it, it like distorts the image. That's a CRT. That's exactly what I have up here. So I'm going to show you this experiment. So basically what J.J. Thomson did was he generated electrons into a cathode ray tube. But the thing is he didn't know that they were electrons. I'm calling them electrons. We know what they are, but he didn't know what they were called. Okay, they didn't have a name yet. So he generated this mystery stream, this mystery ray. And he did a couple things to that ray and saw different observations. He took a magnet to the ray and he saw that the ray was deflected. Okay. He also saw that, so it was deflected by an electric or a magnetic field. And he also determined that this particle or this ray had mass to it. So I'm going to show the demonstration here. So let me just turn off like the lights a little bit. Too much? Good enough. All right. So let me show this demonstration. So we got all those down. So let's look at the observations of the cathode ray tube experiment. So I have my CRT, my cathode ray tube. This is the tube. And I just have a power source here, so I'm going to give it energy, and it's going to produce this mystery ray, and we will look at some of its properties. So think of it, don't think of it as electrons, just think of it as this mystery ray. So I'm going to turn it on. Okay. Do you see that mystery ray? Do you see it? It's green? Okay. All right. There's a fluorescent screen here that is making it green. All right. So basically, whatever ray is being generated is going from one side of the electrical, the cathode, the anode all the way to the cathode. So one of the first observations he made was that they travel in a straight line. Do you agree that they travel in a straight line? That whatever mystery ray is being generated here is traveling in a straight line? Okay, good. So they travel in a straight line. He also saw that they could be bent by a magnetic field. So I have a magnet right here, all right? And we'll see what happens. I can't see it. Okay. Is it being deflected? Oh, I can't see it. Okay. So, do you see the ray being deflected? Yes? Okay, so that's the one way where I bring the magnet this way. So I'm going to just flip the magnet over. Okay, and so now this is a different pole of the magnet. So if I tell you that this pole of the magnet is the positive end, what does that tell you about the mystery ray? If this is the positive end that I am adding here, what would the sign, the charge of the ray be if this is positive? Negative. Okay, and then if I flip this, so now this is the negative end of my magnet. Is this observation consistent if I'm placing the negative end? Yes. All right, so this is how he was able to determine that that it could be, since it was bent by a magnetic or electric field, it implied that there was a negative charge because he just kind of adjusted it depending on what side of the magnet he was using to figure out that this mystery ray has a negative charge associated with it. All right, so, but again, we don't know it's an electron yet. All right, so based upon it interacting with the magnet, we could determine its charge. He did another experiment where he determined that if we hooked this up, so this is still, this next experiment, it's still technically a CRT. The only difference is that this bulb that you see right here, There's a cathode and an anode present, so we're still generating the mystery beam, but you just won't be able to see it. What's different in this apparatus is that there's a small pinwheel in the middle of it, and I'm going to turn on the light so you can see it. I don't want that on. Okay. Once I turn this on, go away, spam. Once I turn this on, so it's the same mystery beam that's being emanated. There's just a difference here. Okay, go. Okay. So hopefully you can see this, all right? But the pinwheel is spinning. So if I turn it off, no more mystery ray, and it will stop spinning. But if I turn it back on and produce the ray, it will make the pinwheel spin. So what does that imply about our mystery beam we are generating? It has mass. Would something that doesn't have mass spin the pinwheel if there was no mass? No. So whatever beam that we're generating, it's the same beam that was over here. It does have mass, and we have to use the pinwheel experiment to determine that. Yeah, question? If I stuck my hand, electrons would probably bounce off. Probably not right away. All right, so one thing so the question is, like, would you feel something if you stuck your hand in it? I would imagine it would feel like, I'm assuming that the power is not very, high. Like, have you ever, shocked yourself, right? When you shock yourself, if it's like the winter time, you rub your feet on the rug, you touch a piece of metal and go, and you shock yourself. Basically, what's happening is that you have generated an excess amount of electrons, and you are depositing them, equalizing it somewhere else. And so same idea here. If you stuck your hand in, you might gain electrons a little bit, so it might feel kind of feel like electricity a little bit. But the idea here is that CRTs also generate radiation. All right, so one thing that I told the demo team I didn't need is a Geiger counter that you can actually show that this apparatus generates radiation as well. So I'm not sure if I'd feel it. I don't want to test it though. Okay, so turns a pinwheel implies that this ray is a particle, meaning it has mass. Also, if we left the tube on long enough, that the tube would heat up over time if we left it run for long enough. So that also implies that whatever is being generated is highly energetic. And so the last thing here is, I only have 2 examples of cathode ray tubes. They're made with a certain type of metal, but the idea here is that this phenomenon will happen regardless of what metal this instrument is made out of. It could be iron, it could be copper, it could be titanium, tungsten, any one of those things, we would see the same phenomena. So that tells me that, oh, this property is consistent with all elements on the periodic table. So all of these observations together tell us, hey, there's something smaller than just like the atom that we think of, and it is present in all matter, all right? So those are the conclusions that we come up with, that 1, this mystery beam is highly energetic, it's negatively charged, it's present in all matter, and yeah, it's smaller than an atom. So this is basically discovering the existence of an electron, right? So now we know an electron exists, yeah. Wasn't made out of another atom because probably it was present in all substances. So regardless of what substance, what element that the cathode was made out of, you would see the same exact observations. Does that make sense? So the small, tiny particle is just present in all substances. Yeah. That's true. Well, I was thinking, our anions do exist. The whole idea here that it is smaller than an atom. But these are all great inferences. Okay, so we know the electron exists. Yes. So I think that was her same question. How do they know that it was smaller than an atom? Can I just go to the next slide? Okay. All right. Can I go to the next slide? So the idea here is that J.J. Thomson's experiment was the first of its kind, okay? He discovered the electron, but the problem is that his experiment was not good enough to determine the actual charge of the electron, and it was not good enough to determine the mass of the electron. Because if we knew the mass of the electron, wouldn't we be able to know that an electron is smaller than an atom, right? All right, and that's the question you guys have. But the thing is that his experiment was not good enough to just calculate one of them. What he was able to do was get the mass to charge ratio, or the charge to mass ratio, all right? And so looking at that, he was able to see, that this substance is smaller than an atom because he has this mass to charge ratio from this experiment. So that's how he knew it was smaller than an atom. Okay, all right, so hopefully that answers that question. But what I wanted to get out here is that it was not J.J. Thomson's experiment alone that could completely answer what questions we have about the electron. Specifically, what is the actual numerical value of the negative charge associated with it, and what is its exact mass? All he could do was calculate the mass to charge ratio, or charge to mass ratio. It's the same thing. Yeah.
So you say that you can determine the charge, is that you can determine the exact numerical value?
Yes. Yes, he knew it was negative because of how it responded to the magnet, but he doesn't know the actual numerical value. We only know the charge to mass ratio, meaning whatever charge the electron is divided by the mass of it. We only know the ratio. It's kind of like the density. We only know like the charge density of it. So that was the problem with his experiment. It is going to take an additional experiment from someone else to complete the story. But the idea here is that this experiment proves the existence, that there is something smaller than an atom. So is Dalton's model correct? No, we actually need a brand new model in order to completely explain the existence of an electron. All right, so the big idea here is that we have a charge to mass ratio. That's all J.J. Thomson could do. That's all he could do. All right, and so this is the second experiment. This is the second experiment where we will get a little bit more information about an electron. And the problem is here that this experiment is very convoluted and I can't demonstrate it, all right? So you're just gonna have to follow me. Trust me, Millikan is a genius, and he was able to do this really crazy experiment, and what made him the genius was how he interpreted the data, all right? So, okay, let me set this up for you. So we're still studying the electron. So the oil drop experiment involves this chamber, okay? This chamber that has electric fields on it. So like a magnetic field, right? Like things that are charged will respond to this field. So he has this electric field that he can vary. He can like turn it off, he can turn it on, all right? Okay, so we got this chamber with the electric field. What he did is he took oil and he sprayed it into this chamber. But oil, like normal, if I took like, you know, a spray can of Pam or something, or like olive oil, that is a neutral charged, like there's no charge on those oil droplets, all right? So he's spraying these oil droplets, and at the same time, he's irradiating them with X-rays. By irradiating them with X-rays, those oil droplets pick up charge. Some charge, we don't know how much. It could be 1, 2, 3, 4, 5 electrons, we don't know. Okay, so he's irradiating these oil droplets with charge. Because let's think about it. If I turn on the electric field and I spray oil into the chamber, what's going to happen to the oil? If I don't do any X-ray stuff, it'll just fall, right? Because all those oil droplets are neutral, right? Charge neutral, zero charge. They're not going to be affected by an electric field. So the crazy thing here is that at the same time, when he sprays the oil, he irradiates them with X-rays. So then they pick up charge. So if I have a charged particle in this chamber and I turn on the electric field, in theory, couldn't I suspend one of those charged oil droplets in air, right? Where the oil droplet has a certain amount of mass, it has a force that's wanting to pull down, but because it's charged and it's in an electric field, it's also going to pull up at the same time. So this is what Millikan did. He did hundreds of thousands of trials where he would do this. He would spray oil, irradiate them so they picked up charge, and he would suspend single oil droplets in air. Just single, like just one of them. He would spray a bunch, but only pick up one oil droplet. And then he would do his calculations, and then he would do it again, over and over and over and over again, okay, until he had a bunch of data. And this is the data that we're going to interpret. All right, and so yeah, this kind of summarizes what he did. Is that what he saw is when he picked up, suspended these oil droplets, a number kept showing up. All right, so this is the data. So when he caught one oil droplet, he was able to calculate the total charge on that one oil droplet. He did this by measuring the circumference of the oil droplet. Okay, when he would catch it, he would take like a microscope and like measure it. He would like measure the diameter. He would take the what's the air volume? The volume of the sphere. He would use the density of oil to figure out, okay, how much does it weigh? Take into account gravity, so that's a force going down. He knew the electric field that he had to apply to bring it up. And so all those things together, he was able to calculate the total charge on each of the oil droplets that he caught. So each one of these bars that you see is one trial. So this is 34 different trials he did, but he probably did hundreds, okay? So that's what you're looking at right now, the charge on each and every single oil droplet. Each single one that he picked up. Okay, so I have the data shown in a very specific way. I just moved them around so you can kind of see the staircase, that the oil droplets with the most charge on them are on this side, the ones with the least are on this side. This isn't the order that he actually measured them. I just rearranged them so it's nicer to look at. So what he saw is, okay, he saw, the oil droplets, they can pick up a different amount of charge. So that was kind of like a weird thing. Also, he observed that the charge that the oil droplet could pick up, it's not continuous. Like, it couldn't be any number in the world. There's only specific numbers that he saw over and over and over again, all right? So if in your mind, or in my mind, because I'm not very smart, if I was doing this experiment and I wanted to determine the charge of an electron, maybe I would just take the average of all of the trials. Does that sound like something that like a scientist would do, just take the average of the data? And then like that's the number I report? Don't you do that in lab? You don't take the average of something and then just report it? No? You don't? You should, okay? Most of the time people do. But the idea here is like most people will just take the average and report it. But he understood that the average of this data doesn't make sense. So he didn't do that. That's what makes him the genius, okay? Maybe you would look at the smallest charge in this graph and be like, oh, that's the charge of an electron. He didn't do that either, okay? That actually wasn't the correct answer either. What he actually did is he looked at all the data and he saw that, okay, all of these trials have the same charge. They all have the same charge on the oil droplet. All of these data points have the same charge. All of these ones have the same charge. Do you see what's kind of happening? What do you kind of see the difference between all of these different trials? They all have the exact same increment. And that he deduced is the charge of an electron. Because we don't know this trial right here. I don't know how many specific electrons that oil droplet has, right? But what I do know is that, okay, maybe these oil droplets have 3 electrons. This one has 4 electrons. So the difference here is the oil droplets, they gained 1 electron. Same for the next step, that each of these trials our oil droplet just gained 1 electron. And so what ended up happening is that that charge increment ended up being the exact same number, exact same value in coulombs each and every single time. It was 1.602 times 10 to the negative 19 coulombs, and that is the charge of 1 electron. Yes? Yeah, that's another way to look at it, yes. So this is what makes him the genius. And keep that in the back of your mind, because I'm going to show you an analogy here, all right, in a little bit. So that is how he determined the charge of 1 electron. It's not the smallest value. It's not the largest value. It's not the average of the values. It's the smallest increment between the values. Right? And so using this information, so our colleague here, our classmate said, oh, it's the least common multiple. If you take this charge and divide by these bars, you can actually go back and determine, okay, how many electrons are on each of those oil droplets. Okay, so now that we have the charge of the electron, this is the second experiment we needed to better understand our friend, the electron. So we have J.J. Thomson's experiment where he could only get charge to mass ratio because he's not very sophisticated. Now we have Millikan's experiment where he did determine the charge of 1 electron. So those two pieces of information together, we can calculate the mass of an electron. We need those two pieces together, right? So these are the conclusions that they got. Okay, we have charge to mass ratio and we have charge. So what is the mass in grams? So I'm going to start with Millikan's information, the Coulomb value. So that's the charge of 1 electron. So the idea here is, okay, how can we use this charge to mass ratio? That unit's really weird. It's Coulomb per gram. So let's kind of do a throwback to chapter 1 and with derived units. When there's a fraction present in the unit itself, we can set the top unit equal to the bottom unit with an implied 1. So if we rewrite this unit as an equality, I can rewrite this as 1.7588 times 10 to the 8 coulombs equals what? 1 gram. It's whatever unit is on the bottom gets an implied 1. So I write the equality because now I can clearly see what my options are to multiply and change the unit I want. So the 1.7 number, is that going to go on the top or the bottom? Bottom. Why on the bottom? Cancel out the coulombs. Yes, that's the idea here. Me personally, I can't just look at these numbers and be like, oh yeah, I need to divide by mass to charge ratio. No, I don't know that. I have to look at the units in order to know. All right. So I'm going to put that 1.75 number on the bottom and then 1 gram up top. And so you see the units cancel. What unit comes out? Is that what we want? Yes, it is. Perfect. So we get that the mass of an electron in grams is 9.096 times 10 to the negative 28 grams. So it's tiny. All right. And so now with this information, we know that an electron is smaller than an atom. So back to those questions. Okay. Because now we have a mass of an electron and we see, oh, these numbers are way, way, way smaller than atoms themselves. Okay? All right. So that's just applied dimensional analysis. Yes? So he used 2 electric fields. All right? I kind of skipped over it. Basically, he took the CRT. Yeah, right here, the CRT. So it's the same experiment. And he applied 1 electric field to deflect it. And then he took a magnetic field in the perpendicular direction to like undeflect it. And so with those 2 numbers, okay, how much strength he put in the electric field versus how much strength he had to put in the magnetic field to cancel each other out, he was able to get a charge to mass ratio. Okay, yeah. So that part's not as important. The important thing is that this experiment could only do charge to mass, could not just do charge, could not just do mass. All right, so now we have charge to mass from J.J. Thomson. Millikan, we got charge, and so together those two give us the mass. So let's do a exam question. Has to do with Millikan. So this question says, okay, using this data, how did Millikan determine the charge of an electron using this data? A, B, C, D, or E? So the first number is the proposed charge of the electron, and then the second part is the reason. So what reasoning is correct with Millikan's experiment? A, B, C, D, or E? What do we think? You want to share? D? D. Is that right? D, the increment between sets of trials. Yes, I think that I stressed this enough, that it's the increment, the smallest increment, the stair step between the trials is where Millikan got the charge of the electron. All of the other reasons, they sound like reasonable reasons. Like if we were just doing any old experiment in lab, like all of these sound like reasonable reasons. It's specific, the charge of an electron, because an electron, when we gain one, it's like a specific number, right? Like we can only gain a whole number amount of electrons. So it's that smallest increment that we're looking for. So yeah, the answer here is E. Or sorry, no, it's D. It's D. Yes, can't read, all right? So let me show you my analogy. And this will help. There's a pretty hard homework question about this too. It uses a different unit other than coulombs, and so that's why it's confusing to students. But here, let me use an example. So I sell lemons. I have a lemon store. You want to buy my lemons? Yeah, okay. The problem is that I'm like a really bad business owner. So I don't know how much my lemons cost. Following me? Okay. So my tax person comes to figure out my tax situation. But the thing is, I suck at selling lemons. I don't know how much they cost, so I can't tell them how much they cost. But what I can tell my tax person is, or show them, is my receipts. I can show them the receipts that all the customers make. So let me show you the receipts, and you guys are my tax guy. You're my tax person, and you tell me if you can't figure out how much one of my lemons cost. Okay? So these are my receipt totals. All I can show you are the totals. Okay. Based upon these receipt totals, can you tell me how much a lemon costs? 25 cents. Can we all get that? Did we all get that? Okay. Because the idea here is, can I buy half a lemon? No, I can only buy a whole lemon. So the idea here is if I think, if you pretend a lemon costs 25 cents, that fits with all this data, right? Also, 25 cents is the smallest increment difference between all of these receipts. But it also is consistent with the receipts, right? Where we would get a whole number of lemons out, okay? So do you agree that based upon this data, it looks like a lemon is 25 cents? Perfect, okay. From this data and what you just concluded, can you determine how many lemons were sold in each transaction? Yes, how? How many lemons were sold in that first one? 5, because now we know how much each one costs. Okay, so hopefully that helps with a homework question. That's on, I think it's called like wombats or wingboos or something. It's some weird unit, all right? Hopefully that helps. Okay, so it's, again, the smallest unit. If I put them in order, like an increasing value, you might be able to see it a little bit better, all right? But let me propose this brain teaser for you. Could a lemon cost 5 cents? Could it cost 5 cents? Yes, it could. Yeah. Can this data distinguish whether it's 25 cents or 5 cents? No, it can't. So that's just some food for thought. So the problem here is there might not be enough data. My instrument might not be good enough, my instrumentation. Maybe my vending machine doesn't take anything smaller than a quarter. You know, so the limitation of instrumentation is very important here, and that's what Millikan had to think about too. All right, so yes, it could be 5 cents, but we're assuming, especially if I could get someone else to do the same experiment, we could see if we both get the same conclusions, we can be a little bit more sure in our answer. That's basically what science is. Okay, sometimes we can't be certain, but we should do enough trials over and over so we can get more confidence. Yeah.
Wouldn't it be would it make more sense to assume that it's 25 cents or more to assume that it's 5? Because the greatest common factor would be 25.
It depends. I mean, think about it. So the question is, well, how do we know it's 5 or 25? See, that's the problem. You guys want answers. But sometimes science and the data doesn't give us all the answers. I don't know. Based upon this data, I cannot tell you for sure if it's 5 cents or 25 cents. Because the idea is, okay, if it was 25 cents, that first person would buy five lemons. But if it's 5 cents, how many lemons would they buy? Or 25. What if the lemons only come in packages of 5? You know, so there's a lot of things going on. I can't tell you for certain which one it is, all right? And you just have to be satisfied with that. I'm sorry. What that should propel you to do is either more experiments, okay? Maybe change your methodology, okay? And if you change your methodology of how you came up with the conclusion and you get the same conclusion, you can be a little bit more certain in your answer. If you give the data to someone else and they come up with the same conclusion, then you can be more certain in your answer. That's essentially what science is, okay? And sometimes we have to be satisfied with not knowing the answer, okay? So, all right, so, good, good, good. There's my analogy. All right, so Millikan, charge of the electron. Did Millikan measure the mass of an electron? No, he measured the charge, and then together with J.J. Thomson was then able to calculate the mass, right? Okay. And so how Millikan was able to be confident in his charge of the electron, because it's the same idea. What if the electron was a smaller charge than that? Someone else came up with another experiment to calculate the charge of a single electron using a completely different experiment, and he got the same number. So that kind of gives you more confidence in Millikan's answer within there. All right, so that is the electron. So now we know the properties of an electron. It's real small, smaller than an atom. It's a subatomic particle. It's negatively charged. It does have mass, not a lot, but it does have mass. So let's think about our theories we've already talked about. So does Dalton's billiard ball model, is that consistent with this newly discovered electron? No. Does Dalton's billiard ball model have an electron in it? No, it's this just spherical thing. So that means we need a new model. So yay, the reign of terror of Dalton is over. Now we have this new theory. J.J. Thomson came up with this theory. It's called the plum pudding model because he was British, and that's what they eat over there, okay? But it basically is like a chocolate chip cookie. We need a model that includes electrons. So J.J. Thomson did the most, just like the simplest thing, and he just dotted the atom with electrons. So if you think about it like a chocolate chip cookie, the chocolate chips are the electrons, okay? And electrons are what charged? Negative, yes, they're negatively charged. So the problem is here is that atoms are neutral charge. So if you dot negative charge, don't you also have to spread positive charge around it to make it neutral? So that's what the plum pudding model says, is that the dough of the cookie is positively charged, and then the chocolate chips are negatively charged. All right, that's what the second question is. Plum pudding model includes electrons. How do they know that the electrons are surrounded by positive charge? It's because the atom has to be neutral. All right, so we needed to put that positive charge somewhere. So they just spread it around. Okay, so that's our model now. It's consistent with the idea that, atoms are, indivisible. They're related to the identity of the thing. It includes electrons now. So it includes all the things we know already until more subatomic or more details about the atom are discovered. So now let's transition to, because we know that the plum pudding model is not right? We know it's not right. Yeah, in our mind, I feel like you know what an atom looks like. So let's look at the next experiment, Rutherford's gold foil experiment, to see how we get closer to our actual atom. So we need to talk about radiation, different sources of radiation. So there's 3 different types of radiation particles, rays that we talk about, and that can be helpful to us here. This is why Rutherford won the Nobel Prize. It was on sources of radiation. So there's 3 types, alpha, gamma, and beta. They all have different properties. So the first one, alpha particles, these are positively charged particles. They are essentially a helium atom, a helium nucleus. So it's a helium nucleus, it's a +2 charge. There's 2 protons, 2 neutrons, but it's total +2 charge. So it's a plus charge. Beta particles, they are negatively charged. They're essentially an electron. So they're negatively charged. Gamma rays, see how the name changed? So now it's a ray, gamma ray. So gamma rays, they have no mass. It's literally just pure energy, right? And there's also no charge, okay? So we call it a ray because there's no mass. There's also no charge. Gamma rays are literally just pure energy. So what Rutherford did and what won him the Nobel Prize is he took a radioactive source, a radioactive material that generated alpha, beta, gamma rays, and he sent them through an electric field. Doesn't that sound familiar? Yes. So let's think about how these particles respond to an electric field. So based upon these charges here. So if we look at this, so I'm just going to cover that. Here's the electric field. Here are the 3 different types of radiation sources. So each of those different colors, okay? Based upon this diagram, we should determine, okay, do you see the blue line and the red line? Do you see those? And see how they're attracted or deflected towards those electric fields, or the poles on the electric field. So if you look at the blue one and see how it kind of moves towards the positive part of the electric field, see that? It's like attracted towards it. What does that tell you about the charge of whatever particle this is? It's positive? It's negative. Like charges, they repel. Like charges, the same charge repel, unlike charges attract. So to me, this looks like, oh, that blue line is attracted to positive, so whatever it is negative. Okay, yeah. Then the red line will be what charge? Positive, yes, because you can think about it 2 ways. It's attracted to the negative part, or it's repelled from the positive part. What about the yellow line? No charge, because it's unresponsive. No charge. Very good. No charge. So just based upon their arrangements on the electric field, we can determine their charge. If we look a little bit deeper, we can say something about the masses too. Okay. Specifically, I want you to look at the red line and the blue line. Okay, the red line and the blue line. If both of those rays are in the exact same electric field, the same force is being applied to it, which one has more mass? Let me propose a question before you answer that. If I push over a really big person versus I push over a really small person, who's gonna fall over more? The big person or the small person? The small person, because they have less mass. Okay, look at this again. Both of the red and the blue, they're in the same exact field. The same force is being applied to them. Which one is heavier? The red or the blue? Red, because it's deflected less. Do we all see how we got to that conclusion? Okay, so the red has more mass. More mass than the blue. Is that consistent? Well, first, are the charges consistent with what we defined alpha, beta, gamma? Yeah, they are. Yeah, so let's look at the blue line. The blue line is beta, right? Okay, beta particles, they're lighter. Okay, an electron is much lighter than a helium atom. Okay, so I should have written that here. Yeah, I should have written lighter. Okay, then an alpha particle. Alpha particles, they're positively charged, and whatever is down here has more mass. Okay, so all these observations are consistent with what we see. Gamma rays have no mass, no charge. So the charge, we know that the gamma ray has no charge because it goes unaffected through the electric field. But does that experiment say anything about the mass of a gamma ray? No, because it's not responding at all. We can't compare the mass of the gamma ray to anything else because it's not responding. So we would actually need another experiment to test a gamma ray, and that would be a pinwheel. So based upon what a gamma ray is, if I shot a gamma ray at this pinwheel, would it move? No, because a gamma ray has no mass. So this question that I propose at the end, which one of the subatomic or the radiation sources here will turn a pinwheel? Alpha and beta. Gamma will not. This is a question on your homework that students tend to get wrong. Again, it's because we already know what a gamma ray is. We know it has no mass, no charge. It's just pure energy. So I think the question on your homework says something like, it's something like this, like true or false. Rutherford's experiment determined that a gamma ray has no mass and no charge. True or false? Rutherford's experiment determined a gamma ray has no charge and no mass. It is false, because I set you up for it. Yes, it is false. The reasoning, and you might be shaking your head like, I thought a gamma ray does have no mass and no charge. That's true. But did Rutherford determine both of those? No, he only determined it has no charge. So that's the detail there. Okay, that's why we're in college. Okay. All right. Are we good here? Okay, so those are radiation sources. Why do we care? It's because Rutherford, and this is why Rutherford won the Nobel Prize. He didn't win it for the next reason. This is his gold foil experiment. He used alpha particles. So remember, alpha particles, they have lots of mass. They're positively charged. They're helium nuclei. He used alpha particles to have us learn more about the details of an atom. So what he did is he took the same radiation source, but he just focused on the alpha particles. So imagine we have this alpha particle gun, and we are shooting it at a thin gold foil, really thin gold foil. So the gold foil is literally just held together with like a couple of atoms, right? It's just a couple of atoms thick. And so he shot these alpha particles at the gold foil, and he saw observations that were inconsistent with the current model, which is the plum pudding model. So let's look at the observation. So this is what he saw. He shot the beam of alpha particles at the gold foil, and he saw most of them went straight through the foil. Straight through. And then he saw every so often, like less than 1% of the alpha particles would be reflected, all right, or like scattered from the foil. So let's look into the details there. So these alpha particles, they have a lot of mass, and it's really weird. This gold foil, think of it like a piece of tissue paper, and we're shooting alpha particles, this cannonball, at this piece of tissue paper. And most of them go straight through the foil, most of them. So what the interpretation is that, oh, an atom is mostly empty space. If an alpha particle can just go straight through the foil, past all of those atoms are mostly empty space. Do you agree with that? Okay, like 99% of the alpha particles went straight through the foil. So he's saying atoms are mostly empty space. Okay, so that, good to understand, all right? Like I feel like we can understand that. What was like the crazy thing and what was like the eye-opening observation that was made wasn't that, oh, most of the particles went straight through. It was that a tiny fraction of them were scattered. A tiny fraction of those alpha particles were scattered away. And the interpretation there, that's what we see right here, is that every so often an incoming alpha particle would hit something and get repelled off. If an alpha particle is positively charged and whatever it's hitting, it's getting repelled off, what's the charge of the thing it's hitting? Positively charged, okay. So whatever those alpha particles are hitting that's in a gold atom is positively charged. But the idea here is that the scattering only happened a tiny, 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 tiny fraction. So that means that just a tiny amount of the volume of the atom is this positively charged thing, which means that it's really dense. Does that sound like something we know? That sounds like a nucleus. That the nucleus of the atom, so this experiment determined that the existence of the nucleus of the atom, because most of the particles went straight through, is telling you that the atom is mostly empty space, and that just like a tiny fraction of them got scattered away, they got repelled off, tells us we have this positively charged, really dense nucleus at the center of those atoms. Now does that sound more like the modern view of the atom we know? We have the nucleus with what lives in the nucleus? Protons and neutrons. So based upon that, what's the charge of the nucleus based upon protons and neutrons live there? It's positive. Is that consistent with his thing? With his experiment? Yeah, it is. Because what if the nucleus was negatively charged? Just pretend if it was negatively charged. If you shot an alpha particle at it, what would happen? They would stick together, they would collide, they would be attracted towards one another, all right? So these are the interpretations, the conclusions he came up with from the data that we saw. That's why these experiments are important. It's the tiny details, yeah.
So, but I mean, the atoms still have the electrons moving around them.
They didn't know that yet.
Like,
They didn't.
Why didn't any of the alpha particles too big and the electrons too small?
Yes, that is. But remember, they didn't know that then. So we're just going off of observations. Yes? Protons and neutrons is made out. The nucleus is made out of protons and neutrons. It's the collection of them, yes, yes, of the protons and neutrons stuck into one another, and that is consistent with the idea that, oh, the nucleus, that cluster of protons and neutrons has to be positively charged because all those alpha particles were repelled away, okay? Correct, it's all no, nucleus just means the collection of protons and neutrons at the center. Since they're all close together, it's really dense. All the mass lives there. That's consistent with the model, the new model, which is the nuclear model. That's what this one is. So this nuclear model says that, okay, we have this positively charged nucleus that has protons and neutrons in the middle there. Okay, so if the nucleus is positively charged, that means all of the empty space needs to be negatively charged, right, in order to be charge neutral. So they said that the electrons live there. All right, and that looks more like our modern day view of the atom. So that is my story about the electron. The electron is fun because it's charged, it responds to things. So the next part of the story is the other subatomic particles, okay? Electrons are negatively charged, protons are positively charged. This is not a fun story, okay? So protons, they were discovered basically the exact same as electrons. They used basically neon tubes. I think, was it J.J. Thomson? Yes, J.J. Thomson. He took neon tubes. He excited these hydrogen atoms. He did the same experiment he did with the cathode ray. and determine the charge to mass ratio of a proton, which is essentially a hydrogen atom without an electron, right? He saw that these protons responded to an electric field and a magnetic field because they are charged. So that's basically it. He used the same method to discover protons he did electrons. Again, the story isn't as fulfilling. The neutron was discovered last. Why do you think it was discovered last? There's what? There's no charge, because what do all of these experiments use? Charge, electric fields, magnetic fields, responding to something. So the neutron was the last to be discovered because there was no charge. It's very hard to just sense it because there was no charge available. So yeah, that's basically the other subatomic particles. They're not as fun to talk about. Neutrons, important in nuclear chemistry. They're the reason like nuclear reactors work, nuclear energy work, the atom bomb, the hydrogen bomb, all of those because of neutrons. And so you can see like in our, do I not have a date? 2 decades later. After when? I didn't even put a date in this one. So much longer. I would say like within like our parents' lifetime, the neutron was discovered. Again, because it's hard to sense because it was not charged. But what we see here is that the mass of the neutron is very similar to that of a proton, but the charge is 0. All right, and they live in the nucleus too. They add mass, but not charge. All right, so that is my story of my electron. So let's put it all together, okay? So now we can take the idea of the electron, what an atom looks like, we can take it back out of our pocket and now appreciate it and use that information when we look back at history, how those experiments, how we got those conclusions and changed the view of our model with time. That's the important part for sections 1 through 2. So now, let's use symbols to represent atoms. So now we know that we have these subatomic particles make up our atoms. They're not these indivisible like billiard balls like Dalton said. We have protons, neutrons, and electrons. Protons and neutrons add mass. Neutrons are neutral. Protons are positively charged. Electrons are negatively charged. So with all that information, we can write these atomic symbols to represent any isotope. Oftentimes we use this type of symbolism where the top superscript tells us the mass number. So this is the sum of the protons and neutrons in your nucleus. The bottom number down here is the number of protons in your nucleus. That tells you the identity of your element. Okay, remember, you're always given this periodic table minus the names, just the symbols. So as long as you know the element name, you know the number of protons. So these 3 equations, I would just say memorize them, okay? Because then you can always write any atomic symbol you want based upon if you know the subatomic particles, if you're given the symbol and need to write it. These 3 equations will help you get there. We need to know the identity of the element. That tells you the number of protons. If you're given the mass number, which is the big number in the corner, that's the sum of neutrons and protons. And then finally, the charge. The charge tells you the number of protons minus the number of electrons. Remember, protons positive, electrons negative. Those 2 added up equal your charge. So we'll do some practice here. So here are some different symbols of carbon. The different symbols, these numbers, 12, 11, 12, 13, 14, what piece of information is that? The mass number. This is not the number of neutrons, it's the mass number. So let's go and fill out this table. So how do we get the number of protons for these different symbols? Number of protons. Do we know? Oh, they didn't put the number of protons in the corner. Am I screwed over? No. Where do we get the number of protons? Yeah. Yes, it's always the same if it's carbon. What number is it though? It's the atomic number, it's 6. So it's just as straightforward as that. It's 6 for all of them because the identity is carbon. Another way that you might see this worded is you'll see, oh, this is called carbon 11, where it tells you the identity and then the mass number. So you see carbon 11, carbon 12, carbon 13, carbon 14. For example, all of them have 6 protons. All right, number of electrons. How do we get that? Yeah, so the idea here is, remember, charge equals protons minus electrons. Since all of these are charge neutral, because there's no charge written, the number of electrons has to be the same. Has to be the same, only for neutral substances, right? All right, number of neutrons, how do we get that? Mass number or what two subatomics together? Protons and neutrons. So since we know protons, we just subtract to get neutrons. So the first one has how many? 5. So it's 5, 6, 7, 8. So what we see here, isotopes of carbon. Isotope just means same element, different number of neutrons, so different mass numbers. So these are carbons with different weights, actually. Okay, all right, so let's do some more practice. All right, so here I give you the symbol, the different subatomics. So just remember, the sum of protons and neutrons is what property? The mass number. The charge relates to the number of protons and the number of electrons. All right, so this first symbol, you can call this hydrogen 2, hydrogen 2. Because I don't have a charge listed next to it, you can assume the charge is 0. So how many protons are present in hydrogen 2? 1. Number of neutrons? 1, because the mass number is 2. Minus one of the mass numbers is coming from that one proton, so the other thing must be a neutron. All right, number of electrons. 1, yes. Because protons minus electrons has to equal the charge. There's a +1 coming from that one proton, so you need a single electron to balance it out, and I didn't write the mass number there. All right, the next one, hydrogen 3. So this is tritium. Tritium. The first one is deuterium. It's just a fancy name for the different isotopes of hydrogen. So since this is hydrogen, we know that there's one proton again. The only difference for this isotope of hydrogen is the mass number. It's still a charge 0. The number of electrons is still 1, but this time there's 2 neutrons in order to give us a mass number of 3. So tritium is the heaviest form of water, all right, of hydrogen. Hydrogen 1 is like the normal hydrogen we think of. Hydrogen 2, that's deuterium, it's heavy water. It's actually a lot heavier, heavy hydrogen. It's a lot heavier than hydrogen with no neutrons, and then tritium has 2 neutrons, so a mass number of 3. And so all of those different isotopes of hydrogen actually do have different properties. So I keep saying heavy water because there's a demonstration. Let's think about this. Water is H2O, right? Okay. H2O liquid, so imagine you have a glass of H2O liquid and you put H2O solid in there too. So you have H2O liquid, H2O solid. What do you see? You see the H2O solid, better known as ice. Where is it? At the ice floats? Yes, okay. Sorry if I made it too simple. Remember, I'm a very simple person. Okay, ice floats. Solid ice floats. Solid water floats. Water as an H2O. If you freeze D2O or deuterium, so instead of those 2 hydrogens, you replace it with deuterium, so hydrogen 2s instead of hydrogen 1s. Those ice cubes made with deuterium are actually denser than liquid water. So those ice cubes actually sink with D2O. I think that's pretty cool. And so it kind of shows you the difference in properties of different isotopes that are present. Oh no, low battery mode. Crap, am I going to make it? Yikes. Okay, let's keep going. All right, sodium plus. All right, so sodium, I don't give you the number of protons. Are we screwed here? No, we can get the number of protons where? The periodic table. How many protons? 11, yes. So the other pieces of information here, 22, that's our mass number. And then the plus sign tells us the charge. So the charge is +1. So we should be able to fill in the rest here. How many neutrons are present? 11, because they have to add up to 22. What about the number of electrons? 10, because 11 minus 10 will equal +1. within there. So I like to think, oh, there needs to be one more proton present in order for the charge to be +1. Let's skip to the end here and see if we can't do this last one. I don't give you the symbol, I give you other things. So I give you the number of neutrons, mass, number, charge. Let's see if there's any pieces we can piece together. Okay, I give you neutrons and mass number. Are you trying to answer this? Okay, yeah, so I have neutrons and mass number. So what piece of information can I fill in just with those two pieces? Number of protons. So how many number of protons? 8, is that right? 8, yes. So number of protons is 8 because we need 8 plus 9 equals 17. You agree? Yes. Okay, so now that we have protons, we know what it is. What element is this? Oxygen, yes. Okay, and with the mass number of 17. Okay, how do we fill in electrons? With the charge. So how many electrons are there? 10. All right, and so that will give us our -2 charge, and then there's our symbol for oxygen. You don't need to put the 8 in the subscript, right? Because you already know it's oxygen, you know it's 8, so oftentimes you'll just see the mass number, right? So feel good about those tables? Okay. If you just memorize these 3 equations, you'll just always be right. Right, and how all of those subatomics relate to one another. All right, so we saw here that hydrogen and has 3 different isotopes: hydrogen 1, hydrogen 2, hydrogen 3. Like, how do we prove that hydrogen can have different weights, different mass numbers, 1, 2, or 3, but it can still be hydrogen? That's really weird. So this experiment, it's a mass spectrometer. What we're able to do with this experiment is split different samples based upon their weights. All right, so what we do here is, let's pretend we have a pure sample of chlorine, just the element chlorine. We send it through this mass spectrometer. So what we do is we send our chlorine sample in, we hit it with a lot of energy, the chlorine with a lot of energy, it picks up some charge. We send it through a, what? Once it picks up a charge, we send it through some type of field, an electric field, a magnetic field. What's shown here is a magnetic field. Because what will happen here, if the chlorine picks up a positive charge and we send it through a field, won't it be deflected based upon its charge? But the thing is here is that in a chlorine sample, in a naturally occurring chlorine sample, there's actually 2 different isotopes of chlorine present. There's chlorine 35 and chlorine 37. So what you're seeing here is that each of those pick up a positive charge, but when we send them through some type of magnetic field, they're deflected differently. So the lighter one gets deflected more, the heavier one gets deflected less. And so what we're able to do is isolate the signals from each of those components, the different components of those chlorines that are there. And so that's how the experiment is set up, very similar to how we worked with charged particles previously. But the idea here is what we do is collect how much of the sample contains each of those different components. How much of your sample is chlorine 35, how much is chlorine 37. So that's what we see here in the signal, the mass spectrometer signal. Right? We see 2 different signals, some from chlorine 35, some from chlorine 37. Right? So what I'm trying to show you here is that this graph, what comes out of the mass spectrometer, is trying to tell you, hey, 75% of your sample is chlorine 35, 25% of your sample is the heavier one, chlorine 37. Yeah. There's a tiny bit of another isotope. But this is what I'm trying to get at here. Is when we think about like the mass of a naturally occurring chlorine sample, we're not working with individual atoms, we're working with a big collection of all of the isotopes present. So if we want to take the average mass of these two isotopes, is it going to be exactly 36? If you took the average of these two? You might look at that and be like, yeah, 35 plus 37 divided by 2 is 36. But the idea here is, are these 2 isotopes equally represented? No, there is more of the lighter one. So will the average lie closer to the light one or the heavy one? The light one. So how we calculate it is through a weighted average, where we take into account, okay, how much of your signal is actually the weight of that component. So do you believe me that these are not equal signals? It's not a 50-50 representation? So I'm just throwing out numbers here. I'm saying, okay, 75% of the signal is the light one, 25% is the heavy one. That's just a rough estimate. It's a rough estimate. Do you agree with me, though, that that's kind of what you see here, right? It's not 50-50. It's not the other way. It's not 25-75. It's 75-25. So with these numbers, I can calculate a weighted average, where I take the weight of chlorine 35, so the weighted average, so that this is what I'm calculating right now, weighted average, is equal to the mass of the light isotope, so 35 AMU, or atomic mass units. I'm going to take 75% of that, so 75 over 100. I'm turning that percentage into a fraction. And then I'm going to add the other component, so 37 AMU, this is the heavy chlorine part of the sample, times the percentage it shows up in the sample. So what am I multiplying by? 25%, or 25 over 100. Yes, 25 over 100. So see, what I'm doing is weighting the lighter isotope heavier by using these percentages. So when you calculate this, these values, you get 35.5 AMU. Is that consistent with what we predicted? We said that the average would lie closer to which one, the light one or the heavy one? The light one. Is that what we calculated? Yeah. Yeah, that it's closer to the lighter one. What's the significance of this value? It's just some random number. Look at chlorine on the periodic table. What's the mass of chlorine on the periodic table? 35.45. So we're real close. Remember, this is a naturally occurring chlorine sample. So we're looking at all of the isotopes nature has to give us here. So the average that we see that comes from the mass spectrometer is going to be consistent when we apply weighted averages to the periodic table, because we are never working with individual atoms. We're only ever working with large collections of atoms, therefore the isotopes in their relative abundances. So a couple more minutes. So this is the weighted average. This is the molar mass, or the atomic mass of chlorine, naturally occurring chlorine on the periodic table. So atomic mass on periodic table. When we take the weighted average. All right, so how we get all of these masses off of the periodic table is we use the weighted averages from the different isotopes that exist for all of those different elements, and we multiply them by their relative abundances they occur in nature. So there's two moving parts here. There's isotopic masses. We multiply by their percent abundances, and we sum all of those up to get our atomic masses we see on the periodic table. So the idea here is that the masses you see here, up here, they are the weighted averages of all of the isotopes present. We're never working with just one isotope. Geez, 5%. So a thing that I like to compare this to is how we calculate your grade in this class. Is homework weighted the same as midterms? No, it's not. So all of this information is on our Carmen modules. I give you this spreadsheet on how we calculate the weighted averages of your grade. So here are the different grading categories, and there are the weights off of the syllabus. And in the yellow boxes are just random numbers that I generated. So pretend like that's the percent of all of the categories that you got. So what you see here is that this student, they earned real good marks on homework, lab, and recitation. They're in the 90% range, right? But their midterm grades are about average in the 60, 70% range. So the reason I'm showing this is because this happens every year. This happens every year. Students they'll get this, all right? They'll get these grades and they'll be like, Dr. Nguyen, I earned 100% in recitation. Why is my grade so low? You sitting there laughing because, okay, yes, you earned 100% in recitation, but how much is that weighted? only 8% of your grade. So the proper way to calculate your grade here is that these are the percentage of the points you earned in each of these categories. So yes, you earned 100% in recitation, so you earned 8 percentage points going towards your final grade. So if you take all of these percentages, all right, they're fractional percentages, and multiply to get the earned points, what you'll see in this first category, you've earned 9.5 points of the total 10 points in homework there. If you multiply 20 times 0.92, you get how much? You get 18.4 points. You get all the points in recitation. And what you see here, the values you get, so 9.1, 8.82, the next one is 9.8, and the final, if you earn 69% of the 20% weight, you earn 13.8 points. So kind of based upon these weightings, is your final grade going to be closer to the 90% region or the 60% region? 60, because those midterms are weighted heavier. They are contributing more. And so if you add up all of these earned points, what you get is that this student has a 77.42%. All right, so it is closer to the 60% range. This would put them at a B minus. So weighted averages is essentially calculating your grade as well. So we will do more weighted averages on Monday, because we don't meet again this week. Yeah, I know.